So this talk is about how to reduce the storage requirements to participate in a blockchain consensus protocol. So blockchains like Bitcoin are highly replicated transactional databases. But more uniquely, blockchains with a decentralized consensus like Bitcoin try to broaden the participation in the governance of the database as much as possible so that there's no central actors that have too much control. But like any transactional database, the size of the database grows with use, and in particular, the size of the state that has to be remembered in order to approve or reject new transactions grows as well. And that places a storage burden on the consensus participants, which hinders the goals of decentralization, which is to make it as easy as possible to participate in the governance of the database. Now, the storage burden is due to what I'll call stateful consensus. And let's take a simplified view at the way that stateful consensus works so that we can see how we could change the model to achieve something better. So in stateful consensus, transactions come into the network, and all the participants in the consensus, well, in Bitcoin, they're called miners, so let's call them miners. Let's say there's 4 miners. They listen to all the transactions. They agree on the transactions to be approved or denied, and the point is that they store all the transactions themselves and retain a local log of the entire database of transactions. So more generally thinking about it as a replicated database, everyone who's participating in the consensus stores the entire database. Now, if they want to, at any point in time, check that they're all still agreeing on the same database, well, it's easy to do that. We know how to compress the size of the information if you just want to check that you have the same, you're all storing locally the same thing. You could just produce a hash of that and share that. But let's say that one of the miners wants to be able to store some kind of compressed state of the history of all the transactions that they've seen and use that to still be able to participate in this verification process of checking the validity of new transactions. Now, the transactional database also has rules, like in Bitcoin, a new transaction may spend the same coins that a previous transaction C spent and therefore should be rejected. So this stateless node, right, which is not storing the history of previous transactions or not storing enough information to be able to determine whether this new transaction is spending and conflicts with something that's already in the database or not, how could we design the system to get around that? We'd want to design the system of stateless consensus so that all the miners participating in consensus could store some kind of compressed version of the history of the transactions in the database and still be able to reject invalid transactions or approve valid transactions. So the questions are, how can we design this? Well, clearly, some additional information is still needed, right? So can we design the system so that a transaction comes in with some small additional proof that the transaction is valid against this compressed state that everybody is storing? And what would that proof look like? How would it be generated? And who generates that proof? So what we're trying to design is essentially a separation of clearly the transactions have to be remembered, right? The entire system can't forget all the transactions in the system. Somebody has to remember the transactions. Somebody has to be able to produce those proofs. But we would like to design a system that separates this problem of storing the state or the history of the database and the job of just being able to participate in the consensus and to verify new transactions. So there's some state storage solution that stores the state and produces proofs that the consensus solution can just read from. Now, who would actually be doing the state storage? Well, there's many options. You could think of it as users just store the information that is relevant for their own accounts, right? Users maintain their own account state, and they're able to produce whenever they submit a transaction that involves information in their own account, they're able to submit a proof to the consensus nodes that the transaction that they're submitting is correct. Or you could think about it as the state storage could be load balanced over all the miners, and we could design the system in a way that every miner stores some of the database, but not the whole database, and is able to produce a proof to the other miners that the new transaction is valid. So back to the question of how we design this. So let's take a concrete look at what we need to do in the case of Bitcoin, which is almost the simplest kind of transactional database. Because in Bitcoin, the only thing that the miners need to know is what are the set of spent outputs. Now, in Bitcoin, every transaction references basically all the miners have to keep track of basically the last time a coin was spent, right? In order to spend the coin again, you need to reference the last time it was spent so that you can say, this is the last time it was transferred. It was transferred to Bob. Now Bob is transferring it to Alice. Another way of thinking about this is that you just need to keep track of the records in the database that are valid, and every transaction has to consume valid records and produce new records. So there's a cryptographic technique called an accumulator, which produces a compressed commitment to a set of items. And this is done in such a way that it is possible to produce a proof that a certain item was committed in that set. So what we would do is we would design the transactions so that every transaction references the set of unspent transaction outputs that it consumes and creates a whole bunch of new transaction outputs, and then contains some accumulator proof that the unspent transactions that were referenced were part of this set that everybody agrees on. So let's talk a little bit about accumulators in a little bit more depth. There's an accumulator that you're probably all familiar with, which is the simplest example of an accumulator, and it's a Merkle tree, right? A Merkle tree allows you to produce basically a hash commitment to a whole large set of items, and then you can produce a proof that a given item is in the set by just giving a path up the Merkle tree. And so the Merkle trees have what's called these logarithmic size inclusion proofs, which we can also call membership witnesses. Now, accumulators also have a function that allows you to add to the accumulator and therefore update the hash or digest, whatever you would like to call it, or accumulator state, which I'm notating here as AI. The accumulator has a whole set of items that are in its state, but the head of the state, which I may call the accumulator state, is just referring to this short tag that in a Merkle tree would be the root of the tree. And there should be a way to verify against this small accumulator state, and given a membership witness for an item, that the membership witness is actually valid, right? And in the case of a Merkle tree, it would be verifying the path of hashes up the tree. But there's other accumulators that have smaller openings, such as RSA accumulators. They have constant size membership witnesses. And there's also ones designed based on pairings. So I'm going to go in a bit more detail in this talk into RSA accumulators and the advantages that they achieve over Merkle trees for this particular problem. But let's go back to our picture and see what we would use these membership witnesses for. So the state storage solution that I was talking about is exactly where we would place the membership witnesses, right? Whoever is storing the state of the database, whether it's users who are each keeping track of the membership witnesses for their own transaction outputs that they might reference in their own transactions, or it's load balanced over the whole system and every miner picks a few of the transaction outputs to remember. If you're storing a transaction output, you need to store its membership witness, and when you create a transaction that references some transaction outputs, and you want to prove to the miners who do not have that in their memory and are only storing the accumulator state, then you would give these membership witnesses to the accumulator, to the miners who are storing the accumulator state, and they would be able to verify it using the aforementioned verification algorithm. So if we were to use Merkle tree witnesses, the problem is that the Merkle tree witnesses are quite large as the database gets very large, right? As the set of unspent transaction outputs grows to be very large. With 100 million, say, UTXOs, storing one witness per UTXO would incur about 100 gigabytes just for the Merkle tree witnesses, which you can think about as the communication overhead of the system, because these Merkle tree witnesses now need to be sent around and passed around with every transaction to all the different miners in the system. Whether or not it's the users who are sending it to the miners or the miners are passing it around among themselves, that's 100x in communication. So the desiderata for designing this in a better way is to do it so that we have the same idea where the miners don't have to store anything and can just receive membership witnesses and verify them, but with minimal impact on communication overhead. So we want short membership witnesses, as short as possible, even shorter than, say, Merkle tree proofs, which are already short because they have log depth, but we want even shorter than that. We want to be able to efficiently do updates to the state of the accumulator, because this is also a dynamic set. When a transaction consumes UTXOs, all the miners need to be able to update the accumulator to then delete those UTXOs from the accumulator, or to add the new transaction outputs that were created to the accumulator. And it would be really nice if we could even aggregate membership witnesses together, or create them in a batch for a whole bunch of for a whole bunch of unspent transaction outputs. So that way, and you can't do this with Merkle trees, but that way you would not incur that 100x communication overhead. You would be able to produce a single membership witness for a whole set of unspent transaction outputs that would be referenced in either a batch of transactions or even within a single transaction. So now let's come back to RSA accumulators, and I'm going to show you a little bit in this talk of how we can achieve some more of that some more items on that checklist using RSA accumulators, which we were not able to do with Merkle trees. In particular, the aggregation and the batching. But the first thing that RSA accumulators achieve over Merkle tree accumulators are smaller membership witnesses for just a single item. So the way that RSA accumulators work, there has to be this trusted setup where an RSA modulus is chosen at the beginning, which is the product of two strong primes that are kept secret from the rest of the system, deleted. And I'm not going to go into it, but there are ways of replacing the RSA group with things that do not require a trusted setup, called class groups, but I'm not going to go into that in too much detail in the talk. The accumulator itself, the accumulator state, starts as just some base element in the group mod n, and every time we add an element to the accumulator, we take the previous state head, call it AI, and we have this hash function which can hash the elements that are being added to the set to primes in the range 0 to 2 lambda, so lambda bit primes. And so we just raise the previous state to the power hash of x to get the new state. Now, to delete an item, we take the root of the previous state, 1 over h of x, to get the new one. You can't necessarily do that delete efficiently from the information you have on the slide, but I'll go into how deletes are done in a later slide. The important thing to know is that what is the state after a whole set of items have been added? Well, it accumulates in the exponent of the base the product of the hashes of all the elements. So the accumulator is just g to the power u, where u is a product of these prime numbers, which are the hashes of the elements in the set. Now, what do membership witnesses look like? Well, the membership witness I'm going to simplify and not refer to the hash anymore. So let's just assume that all the items that we're producing membership witnesses for are already prime numbers. So they're already the hash of the element. So X is hash of some other element, and it's a prime. In order to give a membership witness for X, I would have to give you the X root of the accumulator state A. Okay? Now, if you had the whole set S, it would be easy to produce that membership witness. But there's other ways of updating membership witnesses that I'll talk about later, or producing membership witnesses in a whole batch more efficiently than the time it takes to produce one. In order to verify a witness, you would simply take this membership witness and check that it's the X root of the accumulator state. You just raise pi to the X and see if you get back A. Now, non-membership witnesses look a little different. It involves computing these coefficients, A and B, such that A times X plus B times U, where U is the current exponent on the accumulator state, is equal to 1. And that is possible because this element X is, if it's not in the set and it hasn't been accumulated, it should be coprime with the exponent U. And so then you do that, and then you give basically one group element, G to the A, and then one of these integers B, and that can be used to verify, according to this equation, that the non-membership witness is valid. Now there's ways to update once you get a membership witness for an element. If you just want to hold on to that membership witness and keep updating it as the accumulator gets updated, that's possible, and the same is possible for non-membership witnesses. So now let's talk about aggregating membership witnesses, which was one of our desiderata. There's a trick that you can use, again, using those special coefficients that you can do when X and Y are coprime. So if there's two non-membership witnesses for two different elements, which now would be coprime integers, you can aggregate the two membership witnesses into a single membership witness for the two of them. And immediately that already makes a huge improvement to the application that we were talking about. Like if the accumulator is being used for the UTXO set, then when you send a transaction or a block of transactions, you could, instead of producing a single membership witness for every single unspent transaction output that transaction references, you can compress all those membership witnesses into a single one, which will take about just 3,000 bits of overhead. And that proves the validity of all the unspent transaction outputs that your transaction is referencing. You can think of it as all the records that are being consumed by the transaction. You have a very short proof that they're all valid. Now, let's come back to deletion, because I mentioned that deleting can't necessarily, how could we do deletion efficiently, right? So in the original proposals of RSA accumulators, people were talking about using knowledge of the trapdoor in order to do deletions. And that's a setting that may make sense for a different application, but in our setting, it really doesn't make sense. We already might go up in arms about the fact that we have to do a trusted setup. Certainly, we don't want there to be somebody who knows the factorization and to just rely on that trusted party to do these deletions, and that would defeat the purpose of the system. So if without the trapdoor, deletions might not be feasible. However, notice that what is the state of the accumulator after an element should be deleted? Well, it's actually the same as the membership witness for that element, right? So remember that the membership witness for an element in the accumulator, if the element is X, then it's the Xth root of the accumulator state. And that's exactly the same as what the state of the accumulator should be after you delete that item, right? Because you're dividing it out of the product in the accumulator. So if in our setting, a transaction gives membership witnesses for all the unspent transaction outputs that are referenced in a transaction, then all the miners in the system actually have those membership witnesses handy that they can use that in order to compute what the next state of the accumulator should be after removing those now consumed transactions from the state of the accumulator. But what we really want then is also a way of doing that in an asynchronous manner, or now what I would call a batch delete manner, so that different transactions can come in asynchronously, all giving membership witnesses for certain items, and then somebody can take all of those membership witnesses and say, okay, these are all valid membership witnesses. Let me now use these to remove all of these items from the accumulator state in one batch operation. So that's what this batch delete does. I briefly mentioned class groups as a way to replace the trusted setup. I don't want to go into that in any detail here, but just know that there are other possible ways of doing it, but class groups have, of course, need to be studied more in terms of their concrete parameters and also their in order to achieve security, and also their practicality, since they've been used considerably less than RSA has in practice. So the one thing that we really, really need to make as efficient as possible is the verification of membership witnesses. And that's very important for the application we're talking about, because the time it takes to verify these membership witnesses determines the throughput of the system. Users may be submitting transactions asynchronously and taking a little bit of extra time to produce their transactions. That's not the most important thing. But what's the bottleneck is the fact that these miners all need to receive many, many transactions per second and verify all their membership witnesses at high speed, right? So verification of membership witnesses in RSA accumulators is naively considerably slower than Merkle tree verification, since it involves exponentiation in this group with basically 2,000-bit numbers, right? So how could we speed up that verification? Well, we can use a recent trick designed for a different application, but that is now also relevant to this application, called a proof of exponentiation. And the way that this trick works is, if I want to prove to you that x to the alpha mod n is equal to y, where alpha is very, very large, and I want to convince you in a way that does not require you, of course you could just compute this yourself, but the whole point is to design a interactive proof system that would allow you to verify this statement without going through the process of doing this expensive exponentiation yourself. Then you can do the following. Peggy is convincing Victor, then Victor will choose a random lambda bit prime. So lambda is like, say, 128 bits. Send that to Peggy, and Peggy will basically find the quotient and remainder of alpha divided by L, produces group element x to the q, the quotient q, and send that to Victor. And it turns out that that is enough for Victor to verify, based on the fact that this prime was chosen randomly, that with very, very high probability that this statement holds. Now, the work that Victor needs to do is now not to compute the exponentiation x to the alpha, but only to reduce alpha modulo L, okay, to find the remainder of alpha divided by L, which is still linear in the bit length of alpha, but a much faster operation. So in practice, it would make a huge difference. So putting things together, if we look at how you would form a block of transactions in Bitcoin, you have a header which references a whole bunch of spent previously spent transaction outputs, those spent coins, and your transactions all create a bunch of new coins. So we'll call this a set S of basically consumed coins and a set N of coins that are newly created. And then there will be some signatures because Bitcoin also involves, of course, signing of transactions to authorize the transaction. But the important new thing that we're going to add is the miners are just storing a accumulator state in place of remembering the set of unspent transaction outputs. And in verifying a block of transactions, the only thing that they really need to do is to verify that all the items in S in the block of transactions are actually contained in the UTXO set that is committed to in AT. And with the operations that they then need to do are also to batch delete all of the now consumed coins S from the accumulator. So batch delete all of S from the UTXO set, produce a new head of the accumulator A prime T, and then also to batch add all the new ones that are the new outputs that were created. And that is going to go into the transaction block. And in order to then verify this, if you're another miner in the system, and you're trying to verify that this was done properly, you don't have to go do all this work again yourself. You verify the signatures, and you verify one proof of exponentiation for the batch delete, that the batch delete was done correctly, and verify one proof of exponentiation for the batch add. And of course, you also have a proof of exponentiation for membership witnesses too. So take these numbers with a huge grain of salt, but measuring performance on just a MacBook laptop using Java Big Integer library, if we look at Merkle trees and the time it takes to verify basically a Merkle tree inclusion proof, will be about 8.5 microseconds. So the throughput of the system naively would be like, say, 100,000 per second, whereas computing an exponentiation, g to the x mod n, would take considerably longer. But if we look at the verification, right, which is the important thing, and now the miners in the system, they just have to verify these proofs, basically a proof of exponentiation instead of doing the exponentiation themselves. X mod L, for L being 128-bit prime number, just takes about 0.3 microseconds plus some extra 50 microseconds for actually checking that L is a prime. And so that gets, pretty close to the performance that you would get with Merkle trees. So now I just want to say that we can generalize this even more to not just talking about databases that keep track of one set, but we could also do more complicated accounting systems that have a key value store. And actually, Ethereum uses an account-based model where all the state that all the miners need to keep track of are a set of accounts and what the balance is in every account. And for that, you would use something that is similar to an accumulator but slightly different in the sense that it commits to a positional set, right? It commits to a vector and the item that is stored at every position in the vector. And there are vector commitments. In fact, Merkle trees are vector commitments as well. And the difference between a vector commitment is that you open an item at a position. And so we were able to improve on the state of the art of this to basically get, over Merkle trees, smaller size openings, but over the previous solutions that did better than Merkle trees, smaller common parameters for the system. And the new vector commitments are just based on using the accumulators to basically do bit vector commitments and commit to the bits that are set and the bits that are unset. And you can just use the accumulators basically to build a vector commitment and the batch membership witnesses to do it more efficiently. So the takeaway points are that you can use this new paradigm for designing a blockchain consensus protocol that separates out the consensus part from the state storage part. And the themes are, shifting work from miners to users, and lowering the burden on miners, to which you want to make it as easy as possible to broaden participation, so you reduce their work as much as possible. And users also don't have to do that much work, since they're not caring about all the other users' transaction outputs. They can just do a bit more work to maintain their own. So that's kind of the trade-off that you get. And in a more enterprise setting, you can think about it as a way of load balancing the storage of a blockchain, so that you still want to have fault-tolerant, load balanced storage, but not necessarily in the naive, dumbest way, which has every single node store everything. Thank you. That's all. Any questions? Yes.
I have a question. So why RSA as their linear curve?
Yeah, it's a good question. I mean, so it just turns out that RSA is what we need to use in order to design the accumulator in this way. So the key thing about the accumulator that I explained in detail, it requires a group where the order of the group is unknown, which is the case with an RSA accumulator. Whereas with an elliptic curve group, it's easy, everybody knows what the size of the elliptic curve group is. Now, there are other accumulators that work over elliptic curves. In fact, they work with elliptic curves that have a bilinear pairing, and they work quite differently. And they have similar properties to the RSA accumulators, but not exactly the same. In fact, one thing that they require is a large, linear size common parameters that's linear in the size of the set. So if the set of items to be accumulated is small, that could be reasonable. But if the set of items is huge, such as in the Bitcoin setting, it may not be a great idea. Yeah.
So how large are these hash functions to avoid collisions, and what happens if there is a collision, a hash collision?
So how large are the hash functions to
avoid hash collisions, and what happens if you get one?
Okay, well, so I mean, we have normal, like SHA-256 is a collision-resistant hash function, which is just 256 bits. But here we have to have hash to primes, right? And one naive way you could hash to primes is just by repeating, SHA-256 until you hit a prime number. Primes are pretty dense, so. But basically, is that what? So the size of the hash output, or the time it takes to compute it? What are you asking exactly?
The risk is that you get a collision. Two different transactions generate the same hash to prime number, right? Because then you have two of the same thing. You can't distinguish. Isn't that the risk?
Yes. So I mean, in general, for collision resistance, you need 256-bit. Yeah, I mean, 256-bit is typically what you need in order to avoid collisions. But the thing is that it's not, the issue here is not exactly, are you worried about when you're hashing the elements to primes that you get a collision? I mean, one way of thinking about it is that the UTXO set, right, is keeping track of the. You won't be able to, you basically you first hash to you first generate a unique representation of the. Of the UTXO itself. So if you have a 256-bit hash, then that's not going to generate a collision, right? So now you have unique elements, and if you're trying to figure out how to put a set of unique items into an accumulator, that's a different problem. Yeah. In general, though, the hash that you need in order to avoid collisions is just 256 bits. If you treat the hash as a random oracle, that's what you need for collision resistance.
The question is, does the system break if by chance you happen to have a collision?
If by chance you happen to have a collision, then when you need a collision-resistant hash function, then of course, yeah. But the collisions, the whole point of a collision-resistant hash function is that it happens with negligible probability. Yes, still statistical. Yeah.
Any other questions? All right, let's thank Ben.
Yeah.